This heat pump reversing system works because one four-way valve redirects high-pressure refrigerant flow on demand. The clever bit here is swapping indoor and outdoor coil functions seamlessly. A conventional air conditioner cools indoor living space by absorbing heat inside and rejecting that thermal energy through an outdoor condenser coil along a fixed unidirectional path. A modern heat pump functions as a fully reversible air conditioner, dynamically switching refrigerant paths between internal and external heat exchanger coils. If an engineer attempts to reverse this intense fluid flow using simple manual shutoff valves under high operational pressure, the system encounters extreme hydraulic turbulence and pressure spikes. Manual valve gates subjected to steep differential pressures suffer severe mechanical binding, preventing smooth physical movement, while the compressor forces dense fluid through small orifices. Abrupt manual switching creates devastating hydraulic pressure surges, risking catastrophic valve seal blowout and introducing heavy vibration that damages internal compressor reed valves. Simple bypass loops fail completely because high-pressure gas always takes the path of least resistance, bypassing heat exchangers entirely without structured directional fluid redirection. Engineers resolve this initial setback by separating the mechanical actuation force from manual linkages, utilizing internal fluid pressure differential to slide the primary internal valve mechanism. A small electromagnetic pilot valve directs a tiny bleed stream of high-pressure refrigerant gas into end pilot chambers to push the main slider smoothly across internal ports. By harnessing existing compressor pressure differential, the reversing valve accomplishes heavy mechanical movement without requiring bulky external motor drives or complex mechanical linkage arms. This indirect pilot arrangement prevents violent fluid hammer, ensuring smooth, reliable transitions across high and low pressure refrigerant boundaries within the sealed system loop. Because these HVAC systems operate under high internal pressure and high electrical voltage, sealed refrigerant and mains-powered equipment must be serviced by a qualified technician. The bigger problem was maintaining absolute internal sealing across extreme temperature differentials without permitting high-pressure discharge refrigerant to bleed into low-pressure compressor suction lines. During intense winter heating operations, hot discharge gas exits the compressor at high pressure and elevated temperatures, entering directly into the upper port of the four-way valve. Simultaneously, the adjacent low-pressure suction line carries cold vapor returning from the outdoor coil directly back into the compressor intake port at significantly lower temperatures.
These radically contrasting temperature and pressure fluid streams enter immediately adjacent internal chambers inside a single compact brass valve body casting. Thermal expansion differences across the metal housing can distort tight internal tolerances, causing internal leakage that severely degrades heating capacity and degrades overall thermodynamic performance. To solve this severe thermal sealing challenge, engineers designed a four-way reversing valve utilizing a specialized low-friction composite sliding cup inside a precision brass cylindrical body. The brass valve body features 4 exterior copper connection ports, 1 top discharge port, and 3 lower manifold ports arranged in a precise, evenly spaced linear row. The single top connection port is connected permanently to the high-pressure discharge outlet coming directly out of the primary motor-driven compressor unit. The central bottom port is connected permanently to the low-pressure suction line, feeding cold vapor directly back into the compressor inlet port. The outer left and outer right bottom ports link directly to the indoor coil heat exchanger and the outdoor coil heat exchanger, respectively. Inside the brass valve tube, a movable carriage holds a precision composite slider cup that bridges 2 lower manifold ports at any given moment. In standard summer cooling mode, the internal slider cup covers and connects the central suction port to the indoor coil connection port. Hot, high-pressure gas entering the top port is directed straight into the outdoor coil, which acts as a heat-rejecting condenser exchanger. Outdoor fan air blows across the warm coils, condensing the hot vapor into high-pressure liquid refrigerant while releasing thermal energy into the outside atmosphere. This liquid passes through an expansion device, dropping dramatically in pressure and temperature before reaching the indoor heat exchanger coil inside the structure. Inside the building, cold, low-pressure liquid evaporates within the indoor coil, absorbing thermal energy from indoor air to provide effective continuous space cooling. Low-pressure vapor leaves the indoor coil, passes through the internal slider cup into the center suction port, returning safely to the compressor intake. When the thermostat calls for space heating, an electrical control circuit energizes a pilot solenoid coil mounted on the exterior of the reversing valve body. The magnetic field shifts a tiny pilot pin, closing one internal pressure bleed tube and opening the opposite end bleed tube simultaneously. High-pressure discharge gas vents into one end cavity of the main valve body, while the opposing end cavity vents directly to low suction pressure. This creates a massive differential force across the synthetic piston caps attached to each end of the main internal sliding carriage assembly.
The resulting pressure differential instantly glides the entire internal slider carriage smoothly to the opposite end of the precision brass cylinder. In this shifted heating position, the sliding cup now bridges the central suction port to the outdoor heat exchanger connection port. Hot, high-pressure gas from the compressor discharge now flows directly from the top valve port into the indoor heat exchanger coil. The indoor coil now functions as a high-temperature condenser, releasing thermal energy directly into the indoor living space to warm the building. Condensed liquid refrigerant flows through the expansion device to the outdoor coil, which now operates as a cold, low-pressure evaporator coil. The outdoor evaporator coil absorbs low-grade thermal energy from cold ambient outside air, boiling the liquid refrigerant into low-pressure vapor gas. This low-pressure vapor travels through the sliding cup, entering the central suction port to complete the continuous closed mechanical heating loop. High system discharge pressure pushes the sliding cup firmly against the valve bed, creating an even tighter seal as operating pressure rises. By utilizing smart pilot solenoid pressure steering, the heat pump switches operating modes reliably without complex mechanical gears or redundant external valves. This elegant directional fluid control allows one hermetic refrigeration circuit to efficiently heat or cool indoor environments across all seasonal climate demands. Mastering fluid pressure redirection turns a basic cooling unit into a modern, highly efficient all-season heat pump climate control system.